We are still working on 2-7. Here's day 2. Just two questions to look at, 2 problems. All right, we have an application here. The context is kind of like, it's a business one. It's like marketing or production. I got to be really clear on the 2 equations that we have, because only one of them is going to involve solving a non-linear inequality. Okay? And as you often see when you have applications, sometimes the numbers don't come out really nice. You know, when they're just abstract problems that we kind of choose the numbers that we work with to see the concept, the numbers may work out better, but here it's just driven by, you know, the data that this marketing team came across. Okay, they're trying to settle on what the asking price should be for a new calculator that they're producing. Okay, this is probably a lot of data from either other companies or past sales, whatever. They get to this quadratic that we're calling big P. Okay, big P in this problem is profit. Okay, it is profit. That's what they're after. All right. We also have this other linear model that's going to kind of be the last step of the problem. That's little p, which is price. Okay. In all of these problems, X is the number of calculators that are produced. Okay, so there's kind of this intermediate step that we have to make. Okay, based on the profit margins that we want, which is at least 190 million, how many calculators should we produce? We'll get an interval, and then from there we'll get an interval for price. Okay, but here's how it turns into solving a nonlinear inequality. Okay, I'm starting with big P, all right, which is profit. 0.00001 x squared plus 190x minus 2,500,000. Not a bad idea as we're doing this to kind of pay attention to this quadratic. Okay, 2 things that I noticed with that leading coefficient. It's really small, which means this quadratic is like super, super wide. It's not one of those ones that's been transformed and made like taller or skinnier. It's really wide and it opens down. Okay, because it's negative. And I need to find some values for x that will make this, see if I can fit in all these zeros, at least 190 million. Okay, at least. Now, as always is the case with any polynomial, whether it's an equation or an inequality, I want one side to have a 0. So I'm going to subtract 190 million. And that would give me that. And now we have an inequality that we need to solve. Okay? It's nonlinear, again a quadratic. And if you look back in your notes from day 1, you have an example for a quadratic inequality. Okay? It was a factorable one, but we've known all along with quadratics, we've got 2 options. Ideally, we could factor it. If not, we go to the quadratic formula. What I often find on a problem like this is some will see it and just be totally blown away and super confused and say, I have no idea where to take this. Is it the concept side of the problem that really gets you? Or is it these funky numbers? Okay? Because we need to find the zeros of a quadratic. Okay? It's got some strange numbers, but again, we know 2 different ways. Obviously, we're not going to factor this one. The nice thing about the quadratic formula is it takes any numbers for a, b, and c. They don't have to be nice numbers. We just got to plug them in. So that's the approach that we're going to take here. At first, I love putting a little picture with this. Okay, again, here's what's going on. Now, this isn't going to be like super to scale because, again, this is a really drawn out, wide quadratic. But I just want to give a visual of what we're after. we're going to find those zeros, because we know the X values that we're looking for, because this is the number of calculators produced. This is big P right now. We're working with the quadratic. That's big P, profits. Okay? We want this interval that's going to tell us you need to make between this many calculators and this many to hit that profit margin of 190 million. Okay? And from here, I just go to the quadratic formula. Yeah, when I put in the numbers, they're going to look a little funny here. We have b squared minus 4. This could be a stretch to get all these numbers in, because okay, I'm going to have to don't get too freaked out by this. I got to abbreviate. 192.5 million is the best I can do. Not ideal, right? Obviously you're not going to find an M button on the calculator, but negative 192.5 million is what should go there. And all of this would be over 2 times negative 0.00001. Okay? You'll find out when you I mean, and as far as simplifying this, tailor-made for a calculator, right? That's working with these kind of numbers. This is why we go to a calculator. These are just not super easy numbers to work with, but you'll see when you simplify it, they actually come out fairly nice. Okay, it really starts with that square root that just looks terrible. That's got the negative 0.00001 and the negative 192.5 million. That comes out to be 400. So what you end up getting is one of your solutions is 3,500,000, and the other is, whoops, not 4, 5,500,000. Okay. And again, those are in terms of calculators. That's how many they would need to produce. Okay. And again, it's a little bit tricky with the context, but you know, to do this, we really had to solve an inequality involving a quadratic, which is what section 7 is all about. Now we need to switch gears and go over to little p. Okay. And find some prices. But that's based off of how many calculators are produced. So the first thing I would do is go take 3,500,000. Okay. If we were going to sell that many calculators, what kind of price should we ask? And then I will look at 5,500,000. Okay, 5,500,000. Okay, a little bit of number crunching here to do with these to get these prices. These expressions could be thrown into your calculator all at once, though. You can see right here, if to sell 3.5 million, they should think about asking $65 for a calculator. This one's going to be a little bit lower if they're going to sell 5.5 million. Okay, so in the end, we would get an interval as an answer, and the way I'd want to write that would just be, again, this is little p, and this is the final thing the question was asking for. You know, what prices should they ask for? This is kind of what this marketing team was asked to do, is to come up with an interval. And they've got it narrowed down that to hit those profit margins of 190 million, they should think about asking somewhere between $45 and $65. With the information that we had, that's as far as we could go with the price. Okay, we'd need more information to get it narrowed down beyond that. All right, I'm going to show you one more example here. This one does not have a context, and it is a little bit shorter than that other one. Sometimes finding the restricted domain of a function, I'm going to give you a funky one here, can involve a nonlinear inequality. This would take us back to chapter 1, where we saw that taking the square root of a negative or dividing by 0 are like the two common cases where you can get a function that has a restricted domain. Okay, you've got x values that you're not going to get real numbers as answers. There are all kinds of other cases where the context of a problem can restrict the domain. But this doesn't have a context, so we're just saying what x values aren't going to give you answers, real answers. Now I look at this, right, and I'm aware of this case where I take the square root of, any negative number. So the bottom line is, as I look at 64 minus 4x squared, after I plug in that x value, I end up doing that to the number, right? 64 minus 4 times x squared. After I do that, I want to make sure I have a number that's no less than 0. Okay? We end up with an inequality, and it's not linear. Okay? It actually works out that it's not super terrible to solve. Divide both sides by 4, and I get 16 plus x squared. I take the square root, right? It ends up looking a little bit funny that I get plus or minus 4. Okay? Notice I haven't done anything with a graph. Okay? This would be a tough graph for us to put together. But that's the other thing I want to show you in this example is a totally non-graphical approach. Okay? In the first 3 examples I showed you in day 1, it was all very much off of a graph. Okay? Very much off of a graph. I'm not going to do that here. Okay, to see, which method do you like better? Because you could take this approach. I've found my zeros, which you may come across the term in your book called critical points. Those are mostly zeros. If you're doing a rational function, it can be an asymptote too. Okay, what they mean by that is we find these points where the graph can change signs, and it can only happen at those points, right? So from the solving I did, I identified -4 and 4. As far as the y values changing from positive to negative or negative to positive, these are the only 2 places it can happen. Okay, it's not going to happen anywhere else. Okay, so now here's what I have to do: test 3 points. Okay, test 3 points. Let's say, down here in this first part of the graph, you have all kinds of options. You could plug in -5. Okay? You could plug in -5. If you were to do that, you would find y would be -36. Now I mark that interval with a negative sign. Okay? All it takes is 1 point. You could go check any other point that you want, but you're going to see every single y value over there is going to be negative. All right? Then move on to -4 to 4. Okay? I don't have to check any other points that are less than -4 because that's the negative part of the graph. Go in and I'm going to check 2. If you were to plug 2 in, you would see that y is 48. All right, so I know now, because this was, if you look up here, this sign was a greater than. That's what I'm looking for. What intervals of x values give me positive answers? Okay? between -4 and 4. All right. Now I'm going past 4 because I passed a critical value. So it is conceivable. It's not guaranteed it's going to happen, but it's conceivable at this point that once I pass 4, that the graph could change signs again. So I go down and I check 5. Actually, just like when I put in -5, I get -36, and it's negative, which would now tell me for my solutions, it would be there to there, and my final answer would simply be when x is between and including -4 and 4, okay, those are where I'll get positive answers. And so if I end up taking the square root after I plug those numbers in, I'll get positive y values, and I won't be, taking the square root of a negative.